What's up, guys? Back again with another video. In today's video, we will be solving a very dirty integral with an even dirtier trick. This trick is so devious and crazy that it can solve a crazy integral so easily. It's going to blow your mind, and it's also a very great party trick. So let's get into it. So the integral that we are trying to solve is the integral of e to the 2x times cosine of 3x dx. Now this integral is a very dirty integral. It's a very messy one because there is not a very clear way on how to solve this integral, right? If this inside was 2x, we could just do a u sub where u equals 2x and then do integration by parts, right? But since these aren't equal to each other, we can't do that. We could try doing integration by parts without the u sub by using the di method, where we take the derivative of cosine of 3x, and the integral of e to the 2x, the derivative of cosine of 3x is going to be minus 3 sine of 3x. The derivative of that is going to be 9 cosine of 3x, and it keeps going on forever. And the integral of e to the 2x is just 1/2 e to the 2x. The integral of that is going to be 1/4 e to the 2x, and it just keeps going on forever as well. So we would have to multiply each of these terms and add them together, but since it just goes on forever, the di method, which is equivalent to integration by parts, is not going to work very well in our case. So this integral is a very stubborn one. But luckily, there is a very clever trick that we can use to solve this integral in such an easy way. Your calc teacher will not tell you this trick, but luckily, I will tell you guys this trick. So here is how we solve it. So in order to understand the trick, we need to first review some linear algebra. So we know that from linear algebra that we can write vectors in terms of what is called a basis. And we can write a vector as a column matrix where the components of that column matrix are just the coefficients in front of our basis vectors. Now functions also kind of act like vectors. In fact, you can say that a function can be an element of a vector space. So we can write a function like f of x as, say, 3g of x plus 4h of x, where g of x and h of x are like basis functions. And then we can write f of x as a column matrix where the entries are 3 and 4, which are the components in front of our basis functions, which sort of serve as basis vectors for our function. So the main idea here is that our functions can also act like vectors, and we can represent them as vectors. And under this notation, since g of x equals 1 g of x plus 0 h of x, we can represent g of x as 1, 0, and likewise h of x is going to be 0, 1. Now we know from linear algebra that linear operators that act on vectors are matrices. And we also know that d over dx, which is the derivative, is a linear operator since it's linear in its inputs. This means that d over dx can be represented as a matrix. And that is one of the most important concepts in this video, that we can represent our derivative as a matrix. So how do we actually do that? Well, let's say that we have some basis functions, 1, x, and x squared. This means that we can represent 1 as being 1, 0, 0. X can be represented as 0, 1, 0, and x squared can be represented as 0, 0, 1. Now, say we have some function 2x squared plus 3x plus 2. We can represent that function as 2 times 0, 0, 1 plus 3 times 0, 1, 0 plus 2 times 1, 0, 0, because it's just 2 times 1. That gives us 0, 0, 2 plus 0, 3, 0 plus 2, 0, 0, which just gives us 2, 3, 2. And then we can write that out as 2 times 1 plus 3 times x plus 2x squared, which is exactly what we originally had for our function. So that's how we can write a general function in terms of these vectors, and we can use this to motivate us writing the derivative as a matrix. So to write our derivative as a matrix, what we have to do is take the derivative of each of these basis functions. So the derivative of 1, we know that's 0, right? So it's going to be 0 times 1 plus 0x plus 0x squared. And the derivative of x is going to be 1. So that's just 1 times 1 plus 0x plus 0x squared. And we know that the derivative of x squared is going to be 2x. So that's just 0 times 1 plus 2 times x plus 0x squared. Now what I've done is I've color-coded the components of the results of the derivative acting on each of these basis vectors. And the matrix form of the derivative, which I will call just big D, is going to be 0, 0, 0, 1, 0, 0, and then 0, 2, 0. So this is our matrix form of the derivative. And we see that we found this matrix by just putting our components of the derivative acting on each of the basis vector inside one column of this matrix. And to see that this derivative as a matrix actually makes sense, let's actually use it. So you know that the derivative of 2x plus 1 is going to be equal to 2, right? So in matrix form, that's going to be 0, 1, or let's make it a bit more smaller. In matrix form, it's going to be 0, 1, 0, 0, 0, 2, 0, 0, 0, acting on 2x plus 1, which is going to be 2 times 0, 1, 0, plus 1, which is going to be 1, 0, 0. This is going to equal 0, 1, 0, 0, 0, 2, 0, 0, 0, times, that's going to give us 1, 2, 0. And if we carry out this matrix multiplication, what we will end up with is going to be 2, 0, 0. And that's just going to be 2 times 1 plus 0 times x plus 0 times x squared, which gives us 2 as we expected. So this is the correct procedure to actually build out the matrix form of a derivative. Now here is where the cool part comes in. We know that the integral is just the inverse of the derivative, right? Since the integral of f prime of x is just going to be f of x. So basically, since d is the derivative, this means that the inverse of d is going to be the integral. So since we've covered these concepts, we are now ready to actually solve our pesky integral. So using what we've just learned, we can now calculate this integral in a much nicer fashion. So here is going to be our basis functions that we are going to be using. So e to the 2x cosine of 3x is going to be mapped onto 1, 0. And e to the 2x sine 3x is going to be mapped onto 0, 1. So what we want to find out is what the derivative operator is going to be mapped onto. Like, what's the matrix form of the derivative operator? Again, to find that, what we have to do is take the derivative of each basis vector. So the derivative of e to the 2x cosine of 3x, we know that that's just going to be 2e to the 2x cosine of 3x minus 3e to the 2x sine of 3x. And then the derivative of e to the 2x of sine of 3x is going to be equal to 3e to 2x cosine of 3x plus 2e to the 2x sine of 3x. So again, we have color-coded the components of the action of the derivative acting on our basis vectors. So this means that our derivative, or represented as a matrix, is just going to be 2, -3, and then 3, 2. So since this is going to be our derivative as a matrix, that means that the integral is going to be the inverse of d, which is 1 over the determinant of d times 2, -3, 3, 2. And the determinant is just 13, so we have 1 over 13 times 2, -3, 3, 2. And here is going to be how our integral is represented as a matrix. So now what we can do is we can just take our original function that we had at the top, put it down, and we know that this part inside the function is represented as 1, 0, right? Because this is just 1 times e to the 2x cosine of 3x plus 0 e to 2x sine of 3x. And you just put these entries in the column vector, right? So since that's 1, 0, and we know that our integral is 1 over 13 times 2, -3, 3, 2, our answer to this integral just reduces down to just multiplying a bunch of matrices together, and that's it. So by multiplying these matrices together, we get 1 over 13 times, we're going to get 2 at the top, and we're going to have 3 at the bottom, and here is our answer. And now we have to write it back into our function form. And remember that e to the 2x cosine of 3x, that was just 1, 0. And the e to the 2x sine of 3x was just 0, 1. Meaning that this expression that we have found is just going to be equal to 1 over 13 times e to the 2x, 2e to the 2x, 2e to the 2x cosine of 3x plus 3e to the 2x sine of 3x. And this is our answer to our integral. That's it. We didn't have to use any u sub, integration by parts, any crazy, nasty way of solving it. All we just did is we have written our functions as matrices, and by doing that, the integral just came out to being multiplying matrices together, and we got our answer. That's the trick. This trick is just like, maybe it's just me, but this trick is just so crazy. Like, it's just insane how we can take a complicated integral, we can write the components in terms of vectors, write the integral in terms of a matrix, and just multiply those together, write them back into the function form to get our result. So yeah, here is our answer. Let me write it in a bit more neater fashion. So that is our answer. Let's use this trick for another function. So let's use this method to solve this integral over here. Here it's a bit more clearer which basis functions that we should choose. We can let e to the x, x e to the x, and x squared e to the x be our basis functions. And we can see each of them inside our integral right over here. This means that the inside of our integral, 2e to the x plus 3x e to the x minus 4x squared e to the x, can be represented as just 2, 3, -4. So to find our derivative operator, all we have to do is take the derivative of each of our basis vectors. Now what we have done here is we have color-coded our coefficients like before. So our derivative operator is just going to be 1, 0, 0, 1, 1, 0. Just go straight down or straight across, however you say it. And then 0, 2, 1. So that's our derivative operator represented as a matrix. This means that the inverse of D is going to be this right over here if you were to calculate it. And remember that our integral that we wanted to find was this one right over here. So we move that down. And what's in the inside, that's just 2, 3, negative 4. And our integral is just 1, negative 1, 2, 0, 1, negative 2, 0, 0, 1. So we'd have to carry out this multiplication, and that's going to give us negative 9, 11, negative 4. So we just put this back into our function form to get negative 9 e to the x plus 11 x e to the x minus 4 x e to the x, or what was it? Yeah, it should be minus 4 x squared e to the x, since those were our basis vectors. So yeah, that's just our answer to the integral. It's that simple. It's so crazy how easy this is. Now the alternate form to solve this integral would be to use integration by parts, right? So let's just show you. Let me show you guys the other way of doing this. So the other way is we just take the integral of each term, right? So the integral of 2e to the x, that one's pretty easy. It's just 2e to the x, right? And the integral of 3x e to the x, that's just going to be, okay, so to do this one, that's just 3 times integral of x e to the x. We'd use the DI method here, where we want to take the derivative of x and integrate e to the x. So we have plus, minus. The derivative of x is just going to be 1, then we get 0. Integral of this is just e to the x, e to the x. We go straight across. So that gives us x e to the x minus e to the x. Okay, and for our fourth integral, you want to find out what negative 4 times the integral of x squared e to the x's. We should have a dx in all of these integrals, by the way, but I was just being a bit lazy. Again, we use the DI method for that. We have plus, minus. We want to take the derivative of x squared, integrate e to the x. That just gives us 2x, then 2, then 0. Here we'd have e to the x, e to the x, e to the x. So then we just go straight across, giving us x squared e to the x minus 2x e to the x plus 2e to the x. So now we have to combine all of our integrals together. So remember that here we had a 3 multiplied by all of this, and we found out that it was this. So the integral should be 3 times that. So it's going to be 3 times x e to the x minus e to the x. And then the previous one, which is 2e to the x. And our last one was negative 4 times the whole thing. So we have to multiply this by a negative 4. So what we have is negative 4 times x squared e to the x minus 2x e to the x plus 2e to the x plus 3 times x e to the x minus e to the x plus 2e to the x. So if we were to distribute all of these things, we'd get, and then combining like terms, this is going to give us negative 6e to the x. This is going to give us negative 9e to the x. And then this is going to give us 11e to the x. So we have negative 9e to the x plus sorry, this should be 11x e to the x. So we have negative 9 e to the x plus 11x e to the x minus 4x squared e to the x. And what do you know? That's exactly what we have right over here. So yeah, take which one that you prefer more. Like the DI method here, which is just integration by parts, it took us more steps. It was much more algebra to get our answer. So, but our other method that we learned now, it's much more nice. It's just multiplying matrices together to get our answers. We don't have to take the derivative, integrate multiple times, and combine them for each one, then go through all that messy algebra. It's just so straightforward. So yeah, that's the method to find the integral by using linear algebra. Now, there are a couple of things that we have to go over, and there are some limitations of this method. So we want to find this integral, right? And we did. But there is a caveat here. So this method only works when the derivative of the vector that's on the inside is a member of the vector space. And our vector space here is just the span of the vectors ex, x e to the x, and then x squared e to the x, right? So, and the derivative, right, operator, it is going to be in the span, because the derivative of this term over here is going to be, or let me make this a bit more nicer to read. The derivative of what's in the inside is going to be 2e to the x plus 3 times e to the x plus x e to the x minus 4 times 2x e to the x plus x squared e to the x. And you guys can see that if we just distribute all these on the inside, this is going to be in the span of our vector space. So that's why we are able to do this, because our derivative acting on the vector will actually be a member of the vector space. But if we had something like the integral of 2e to the x plus 4e to the x squared, we will not be able to do this method, because the derivative of the inside is going to be 2e to the x plus 4, so plus 8x, yeah, plus 8x e to the x squared. And this is not going to be in the span. It's not going to be in the span of e to the x and ex squared, because we have an 8x here, and there is no x e to the x squared term here. So we cannot use this method for this case over here. So we can only use the method when the derivative of the term that we are integrating is going to be in the vector space that is spanned by the basis vectors that we choose. That's just an important aside there. And now let's actually talk about why what we're doing actually works. And to do that, we have to do some group theory. Now, for those that don't know group theory, you can just ignore this part of the video, but I'm going to include this for this video to be a bit more complete and self-contained. So basically, let's go back to 1x and then x squared. And basically, we mapped 1 to 1, 0, 0. We mapped x to 0, 1, 0. And we mapped x squared to 0, 0, 1. What this mapping actually is what's called an isomorphism. It's an isomorphism between these polynomial functions and between vectors in R3. And we know from group theory that an isomorphism is a bijective function f, where f acts on A operated with B, which gives us f of A wedge f of B, where A and B are members of some group G, and f of A and f of B are members of group H, where f is mapping elements of G to H, and then this operation is in this is a group operation for G, and here is a group operation for H. So that's an isomorphism. And it's basically telling us that we are making a mapping between two different kinds of groups that are very similar. In fact, they are so similar that we can pretend that one is the other. So basically, what we've done here is we are making a mapping that are and where we are taking polynomials and we're mapping them onto vectors. And and how these vectors act, they're going to act in the same way that the polynomials act. And that's going to give us a nice isomorphism that we can use to solve our integrals. So for those that don't know about isomorphisms, I made a video on that a while back in my group theory playlist. But to prove that this is an isomorphism, basically what we have to do is take the function of these basis vectors, like 1 plus x, and show that that's just equals to f of 1 operated with f of x. In this case, it's just going to be plus, because the group operation that we are considering here is the group under addition, not multiplication. If you use multiplication, it's no longer going to be an isomorphism. But it's a nice exercise to prove that this is going to be an isomorphism. So by making an isomorphism, we can treat these functions as vectors, and then we can solve integrals pretty easily. So yeah, that is pretty much it for this video. There are a lot of cool applications for this method, and I really recommend checking those out. So yeah, that's how we solve dirty integrals, but just using linear algebra. Thanks for watching and have a great day. Bye.